highway practice, an abrupt change in the vertical direction of moving vehicles should be avoided. Now, in order to provide a gradual change in its vertical direction, a parabolic vertical curve is adopted on account of its slope, which varies at a constant rate with respect to the horizontal distances. Now, in vertical parabolic curves, we have the following major rules. Now, first, the vertical offsets from the tangent to the curve are proportional to the squares of the distances from the point of tangency. Now, this first rule is based on ratio and proportion. Now, let's say we have a triangle, and then let's say this is our origin, and then here we have a parabola. Let's just consider this as a linear function. So let's say this is x, this distance, and this is y, while this is x and this is y. And then let's pick a point, let's say right here and right here. Let's say this is the height and this is the base, while this is also the height and this is the base. This distance as well as this one, that will be our base. And so by ratio and proportion, we have to use the following rule. Now, if y is to x for triangles, we know that this will correspond to the height divided by the base. However, this isn't true for spandrels or parabolas. Now, this is because for spandrels, by the way, spandrels are taking this shape. For spandrels, our ratio and proportion for the horizontal distance must account for the degree of the curve. Now, let's say this has a degree of 2. And so what's going to happen is we have y is to x squared equals h over b squared. Now, this is squared because our degree is 2. If our degree is 3, then this is also 3. And so essentially, our ratio and proportion must be y over x to the n, in which n is the degree of curve. This is equal to h divided by b to the n. Now, for triangles, since the function is linear, this has 1 right here, and this also has 1 because the degree of curve is actually 1. And so this is the concept that you have to remember. Now, next, the curve bisects the distance between the vertex and the midpoint of the long chord. Now, this is our vertex, and then this is the midpoint of the long chord. And so this actually is a dividing line of this orange line, and then it divides this line into 2. Now, next, if the algebraic difference in the rate of grade of the two slopes is positive, that is g1 minus g2 equals positive, we have a summit curve. Now, a summit curve takes the form of this figure because this is our curve, it concaves downward, and then we have a highest point, which we'll label as, let's say, HP for the highest point. Now, this is when g1 minus g2 is positive. However, if g1 minus g2 is negative, then we have a sag curve. Now, a sag curve looks like this. Instead of a highest point, we will have a lowest point. And so this will be our tangent line, and also this one. And then let's say this is the lowest point of the parabola. And so this will be LP. This is a sag curve. Now, fourth, the length of curve of vertical parabolic curves refers to the horizontal distance from the PC to the PT. And so, unlike horizontal curves wherein the length of curve is the arc length, our length of curve is actually the horizontal distance from PC up to PT. And so L right here, since this is the horizontal distance from here up to here, then this is now our length of curve. This is something you must remember. And then here in parabolic curves, we can't apply formulas involving circular shapes because we are now dealing with a parabola, not a circle. Now, next, the stationing of vertical parabolic curves is measured not along the curve, but along a horizontal line. So recall that in horizontal curves, our stationing is along the curve. Let's say this is an arbitrary station, and this is another one, and so on. So it's along the curve. However, for parabolic curves, our stationing is along the horizontal distance. And so let's say this is a certain station, and this is another station, and so on. So it's measured horizontally. And then for a symmetrical parabolic curve, the number of stations to the left must be equal to the number of stations to the right of the intersection of the slopes or forward and backward tangent. And so what makes this a symmetrical parabolic curve is this dividing line. If the horizontal distance from this line up to PC is equal to the length of the horizontal distance from this line to the PT, then it's a symmetrical parabolic curve. And so this is our point of intersection. Let's say this is PVI, or the point of intersection of the vertical curve. If we will draw a vertical line from here and then extend it down, this is L over 2, and this is also L over 2 for vertical parabolic curves. Now, if this length is not equal to this one, then we have an unsymmetrical parabolic curve, which we will discuss in another video. And then next, the slope of the parabola varies uniformly along the curve. Now this is because the general equation of a parabola with the vertex at the origin is y is equal to kx squared. And so if we will differentiate this, then this will be dy over dx is equal to 2kx if we'll differentiate this with respect to x. And so differentiating this once more, we now have d squared y over dx squared. This is the rate of change of the grade or slope. And then finally, the maximum offset h, which is this distance from here up to here and also up to here, that's equal to 1 over 8 of the product of the algebraic difference between the two rates of grade and the length of the curve. And therefore we have h is equal to 1 over 8 multiplied by L times G1 minus G2. Now for the purpose of discussion, we'll be deriving this formula. Now in our figure, G1 and G2 defines the slope of the back tangent and the forward tangent respectively. And so if this defines the slope, then this is equal to rise over run. Now just so that you can see what this is, let's say we have a triangle, and then let's say this is 3 while this is 1. So our rise over run will be the slope. And so since our rise is 1, we have 1 divided by the run, which is 3. And so this is the simple definition of a slope. However, here, G1 and G2 are expressed in percentages. And so you can usually see G1 equals 3% or G2 equals negative 2.3% and so on. These are your possible values. And so now, since this defines the grade, this means that grade is equal to rise over run. And so let's just say this is y, or the height, while this is x. So we can compute the height or the rise by multiplying the grade or the slope with the horizontal distance or the run. So we have rise is equal to grade multiplied by run. Now we will be using this concept in deriving our formulas. Now first, let's try to make a formula for this distance h. Now this is also another concept for vertical parabolic curves. The distance from PVI to a point on the curve along a vertical line from this point, that's equal to h. And then if we'll also draw a line from the midpoint of the long chord up to the same point on the curve, then that distance will also be h. And so let's try to solve this value because this will be important in our calculations. Now what we can do first is we can extend the back tangent. Let's extend this indefinitely. So let's say up to here. And so what we're gonna do next is from the PVT, let's draw a vertical line. So this is our vertical line, and then from PVI, let's draw a horizontal line up to this point such that they will intersect. And so let's draw a line here up to this point. We can now use this triangle in order to derive an equation for h. Now let's say this is the point of intersection of this line and this line, which is the back tangent. Now we have defined that rise is equal to grade multiplied by run. Now, if the grade of the back tangent is G1, then the grade of this line must also be G1 because they are both along the same line, so they must have equal slopes. And so if this is G1, then the rise, which is this value, this must be grade multiplied by the run. And so the grade is G1 multiplied by the horizontal distance, which is our run. So that will be, let's try to look at the distance from this line up to this line. Notice that it's just equal to L over 2. And so this is multiplied by L over 2. And so next, if we'll extend this line up to PVT, then the rise will still be equal to grade multiplied by the run. Now our grade right here is minus G2. And so this is the grade multiplied by the run, which is still L over 2. So times L over 2. So these are now our distances. And so the total length from this point up to this point, this will be, since L over 2 is common, we can say that this is G1 minus G2 multiplied by L over 2, the distance from this point up to this point. Now by the way, this is positive because we have an ascending grade, while this is negative because we are going down, or we have a descending grade. And so this will be our sign convention. This is ascending because this is going up, and this is descending because it's going down. And so take note of this. And so let's just remove this. Now the next thing that we have to do is we can label these points. And then let's try to look at the triangles that we can form. So let's say this is A, this is B, this is C, this is D, and this is E. Now, I believe you would agree that triangle ABD is just similar to triangle AEC. Let's use another color. This is triangle ACE. And so as you can notice, these are similar triangles. Now first, let's look at triangle ABD. So from triangle ABD, by ratio and proportion, let's try to relate the height with the horizontal distance that it covers. And so for triangle ABD, our height is equal to h plus h, which is 2h. So this is 2h divided by the horizontal distance, which is L over 2. So this is L over 2. And then for triangle ACE or AEC, we have a height of G1 minus G2 multiplied by L over 2. So this is, let's say this is BD. Let's just change it later. This is BD over this length, BD over L over 2. This is equal to this length, which is segment CE, divided by the horizontal distance that it covers is the length of the curve, or L, because it's from PVC up to PVT. So this is over L. And so we can now change these. And so BD is equal to 2h. So this is now 2h over L over 2. While we have CE equal to G1 minus G2 multiplied by L over 2. And then this is over L. Let's just move this. And so now, simplifying this formula, we want to get h. And so let's multiply the reciprocal here. The reciprocal of this one, this is L over 2 divided by 2. And so we can now look at what will cancel. And so this will now be removed. And then this will cancel. And then we are left with h is equal to G1 minus G2 multiplied by 1/2 times L over 2 all over 2. And so since this is in the denominator, we can just multiply the reciprocal of this value to the numerator. And so moving this will now become 1/2. And so we now have h is equal to G1 minus G2 multiplied by L for this one. And then at the bottom, we have 2 times 2 times 2, which is 8. So this is now L over 8. And so this is now our formula for the maximum offset value, which is h. And so that's where this comes from. And so now, we already have our first important formula. And so next, what we are also interested in is the location of the highest or lowest point of the curve. Now this is important because if we can locate the highest point or the lowest point, it will be the ideal location of some of our pipes or control structures. Now let's say we have a sag curve. This is the curve through which vehicles will pass. And so the lowest point will usually determine the location of culverts or maybe some pipes in our drainage systems. Let's say this is the lowest point. Usually our pipes are located right below this point. And so let's say we have this pipe. The elevation of this pipe is determined from our calculations of the lowest point. And so we need to find this distance. Let's say this is S1. Now this horizontal distance is from PVC up to the lowest point. And so here, since we have a summit curve, then the distance from PVC up to the highest point, that will be our S1. So let's say this is S1 and this is S2. Now, what we are going to do here to simplify things is we'll draw our axes right at this point so that the location of the vertex will be at the origin. Now recall that if we have a parabola in which the vertex is located in the origin, then the general equation for this parabola is y is equal to kx squared. And so this is what we're going to mimic. And so we have here our axes. This is y and this is, let's say, x. So this is now our origin. And so we can now make relationships from this figure. Now recall that the first derivative of a function is the slope of the tangent line for any point on the function. And so we'll recall this concept. Since we know the slope, which is g1 for the back tangent, and then for the forward tangent we have minus g2, then we can take the first derivative of this function so that we can identify the slope. So taking the first derivative with respect to x, this now becomes dy over dx is equal to 2kx. Now recall that dy over dx is simply the change in y with respect to the change in x. And so this defines our slope. Now since the slope corresponds to the grade, then we can actually change this into our grade. And then x right here is the horizontal distance. And so first, we can look at S1. This is our horizontal distance. And then for S1, our slope is equal to G1. And so here we now have G1, which is dy over dx. Let's just copy this. This is for our first equation. This is now G1 is equal to 2k multiplied by x, which is S1. So this is times S1. And so this is our first relationship. Now for S2, we have the slope equal to G2 minus G2. And then our distance along x, or the horizontal distance, is equal to S2. So for our second relationship, we have, let's just move this, we have minus G2 is equal to 2k multiplied by S2. Now remember that if you have two equations and then you want to find a variable, then you can divide both equations and and then see what you can cancel. And so let's say this is equation 1 and this is equation 2. So dividing equation 1 by equation 2, we have, since this is on the left hand side, this will now become g1 over minus g2 is equal to 2k_s1 divided by 2k_s2 for the right hand side. And so as you can notice, 2k will cancel, and so we are now left with g1 is equal to s1 divided by s2 multiplied by minus g2 if we are to move that here. And so we are now running out of space, and so let's just move this. And so here, notice that we still have two unknowns. We have s1 and s2. However, we can express s2 in another way. Notice that L minus s1, that's just equal to s2. So therefore, s2 is equal to L minus s1. And so we can now change this. We have g1 is equal to s1 over L minus s1 multiplied by minus g2. And so multiplying this here, we have g1 times L minus s1 is equal to s1 times minus g2. And so expanding this, we have g1L minus gs1 equals, let's just move this to the front. This is minus g2 times s1. And so here, if we'll join the common terms, we need to move this to the right side. And so moving this, we have g1L equals minus g2 times s1 plus g times s1. This is g1. And so we can now combine the like terms. So we have g1L, or now let's just place a parenthesis, g1 times L is equal to s1, let's factor this out, multiplied by negative g2 plus g1. And so dividing both sides by minus g2 plus g1, this will now cancel. And so our formula for S1 will be G1L divided by minus G2 plus G1. However, to make this equation better, we can just move G1 to the left and minus G2 to the right. And so this now becomes G1 minus G2. This is now our second important formula. And so now, let's also try to derive a formula for S2. So we know that S2 is equal to L minus S1 as defined right here. However, since we already know S1, then this now becomes G1L divided by G1 minus G2. Now we can take the least common denominator, which is just simply this expression because the denominator of this term is 1. So this is now 1 multiplied by G1 minus G2. And so this expression divided by this expression, that will give us G1 minus G2. And then multiplying that to the numerator, we have G1L minus G2L if we will expand it. And then for the second term, we have, let's take the sign, which is minus, and then G1 minus G2 divided by this expression, that will give us 1. And so 1 times the numerator, that will be G1L. And so this is G1 times L. And so notice that this will cancel. And so we are now left with minus G2L divided by G1 minus G2. And so to get rid of the negative sign, we can factor out a negative right here. So this now becomes minus G2L, and then we have minus multiplied by negative G1 plus G2. And so this will now cancel. And so reordering this, we now have S2 equal to G2L divided by G2 minus G1. And so let's just copy this, let's place it here, and also this one. These are now our important formulas. Now for the elevations, since generally we are given the elevation of PVC, then to get the elevation of a point on the curve, then we need this distance. Let's say this is y. Now how are we going to compute y? To compute y, we will use this ratio and proportion. And then since we have a parabolic curve, we need to use a value of n, which is 2. Now the question is, where are we going to relate this? Now let's say this is y1, so this corresponds to x1. And so let's say this is x1 from PVC up to the point on the curve. This is x1, so y1 is to a horizontal distance of x1. However, we need to square this. This is because of the squared property of a parabola. And so we will relate this to known values, which is, for this figure, we know that for the offset h, the horizontal distance is L over 2. And so if this is L over 2, and then this is our offset, then we can say that y1 over x1 squared is equal to h, this one, divided by L over 2 squared, because again, this is the horizontal distance. So we are considering this distance and this distance compared with the offset. And so this is now our general ratio and proportion. And so let's say you have y2 right here, this is y2, and then from PVT, let's say we have a given distance which is x2, then we can also say that this is equal to y2 divided by x2 squared. And so this is what you have to remember. This is for general relationships. And so memorize this one, and also the concept of this relationship. Now just an additional input, we also have this formula. For the rate of change of grade, that's equal to G1 minus G2 divided by N, in which N is the number of stations. Now in our concept, in the previous discussions, we know that one station is equivalent to 20 meters. And so once you get the number of stations, you need to multiply this by 20 meters to find the length of the curve. And so now, since my voice is still recovering, let me just add this sample problem, and then I will just add comments, which will be displayed as text.